Welcome students to the first lecture of thermodynamics. This will be a introduction to thermodynamics lecture. In this lecture we will cover some definitions. We will cover what a system, surroundings and the universe means. We will also talk about thermodynamic state of a system, properties and functions. So to begin with, we have to know what is thermodynamics. Thermodynamics is the branch of science that studies how heat, energy and work interact within physical systems. It explores how energy is transferred, transformed or conserved and how these processes affect matter. So basically thermodynamics studies how energy is transferred from one place to another, and while transferring, does it transform, does it get conserved, and how it affects the places from where it is going and to which place it is coming. And a branch of thermodynamics is engineering thermodynamics. Engineering thermodynamics is the application of thermodynamic principles to the design, analysis and optimization of engineering systems. It focuses on how energy is converted between heat and work and how this transformation affects physical systems like engines, turbines, refrigerators and chemical reactors. So basically we will apply thermodynamic principles to realizable systems and see what we make out of it. Okay, moving forward. So as I have said earlier that thermodynamics basically studies the transfer of heat from one place to another, but which place to where? To understand this, we need to understand what is a system. System is a part of the universe separated from the rest of it by real or imaginary boundaries, and which is the subject of observation and study. So system is that which we observe and study. So what is there apart from the system? That is surroundings. The rest of the universe after the system is appropriately chosen. So a observer, a researcher chooses the system, and once the choosing is done, whatever is left is the surroundings. Then comes the universe, which we have been talking about. So it is a sum total of all the matter and energy. Universe can be understood globally or locally. For example, an isolated magnetic pole has its magnetic field stretched up to infinity. So that is the universal scale, but its effect is negligible after some length is traversed. But if you go a bit away, further away from the magnetic pole, you will feel that there is practically no effect. So when we talk about practical terms, in most cases by universe we mean the immediate surroundings of the system, where the effects of heat transfer can be observed. Moving forward, that let us see this Venn diagram. This Venn diagram appropriately depicts the relation between system, surroundings and the universe. The excuse me, the square box is the universe. The circular area which is not shaded is the system. So the shaded area is the surroundings. The universe composes of the surroundings as well as the system. If you use set notation, the equation will arrive such as system union surroundings is equals to the universe. So when we take all the elements of the system and the surroundings, we get the universe. And if we see whatever is common between system and surroundings, that is system intersection surroundings, is that a null set, that there is a set which has no elements in it. So system and surroundings has nothing common in between them. So these things are the mathematical representation of the relationship between system, surroundings and the universe. The physical relationship has been discussed earlier. So moving forward, we have to ask ourselves what constitutes a system. We have known the definition of the system, but what actually constitutes? What is the system made up of? The system is made up of matter, energy, and the boundary, which can be real or imaginary, and the boundary has to be chosen by the observer. The observer decides the system boundary according to his or her convenience. So this point has, this cannot be further important to be given here is that the observer chooses the boundary. That is, the observer decides what is the system and what is the surroundings. Systems are of different kinds. One is the open system. A system which can exchange matter and energy with the surroundings is an open system. A simple example is a pot boiling water on stove top. The water gains heat energy from the burner and some of it evaporates, turning into steam, which is the matter that escapes into the air. Then there is the closed system. A closed system can only exchange energy in the form of heat with the surroundings. A common example is a sealed pot. You can heat or cool the water inside, energy transfer, but the water itself cannot escape the pot. So no mass transfer with the surroundings. And there is the isolated system, a system which can neither exchange matter nor energy with the surroundings. A thermos flask containing a hot liquid is a good example of an isolated system. In thermodynamics, the thermos flask's insulation prevents heat transfer and its sealed design prevents mass transfer. So energy and matter are exchanged in case of an open system. Only energy is exchanged in case of a closed system, and neither energy nor matter is exchanged in case of an isolated system. Now we have understood what the system consists of and what kind of systems there are. Now we have to ask ourselves in which state a system is in. A thermodynamic state of a system is its condition at a specific time. In thermodynamics, we do not talk about rate. We only talk about the coordinates and how they transfer, how matter changes. We talk about transformation but not at the rate of transformation. That is a subject of kinetics. So a thermodynamic state of a system is its condition at a specific time that is fully identified by values of suitable set of parameters. The parameters include pressure, volume, temperature, composition, refractive index, etc. Then what are thermodynamic properties? What are the properties of a system? In thermodynamics, a physical property is any property that is measurable and whose value describes a state of a physical system. So we have to express the state of a system via some measurable parameters. The thermodynamic properties are described or defined as characteristic features of a system capable of specifying the system state. So when you say the state of a system, what defines the state of a system? It is the properties of the system. The properties can be pressure, temperature, volume, mass, internal energy, number of moles, etc. Then we have thermodynamic function. A thermodynamic function or variable is a property of system which is in transition, thereby making it variable rather than a constant parameter. So listen carefully. So what happens is when I have defined the system is unchanging, then the parameters that define the system is its properties. But suppose heat or energy transfer is occurring from the system or to the system, so the system is changing. What changes actually? The state changes. The state changes is defined by changes in some parameters. It may be pressure, temperature, volume. When they are in a state of the change, they are no longer properties but they are functions or they are thermodynamic variables. So when a system is unchanging, we have thermodynamic properties. When a system is in the state of transition, we call the properties functions. So this is the distinction between thermodynamic properties and functions. Next, let us see what kind of properties a system has. So, one kind of property is extensive property. An extensive property of a system depends on the system size or the amount of matter in the system, like mass, volume, internal energy, enthalpy, etc. To give an example, uh, you can see a 2-liter soft drink bottle is much bigger than a 300 ml soft drink bottle. So here the volume is proportional to the size. You can gauge the size that the 2-liter bottle is much bigger. So that is why volume is a extensive property. Then there is the intensive property. The properties of a system that do not depend on the size or quantity of matter in the system in any way are referred to as intensive properties, like pressure, density, concentration, chemical potential, refractive index, etc. Again, let me give an example. Suppose you take a cube of iron. Its density will come around 9 gram per cc. Then you take a small piece out of that block and measure its density. Its density is also will also come about 9 grams per cc. So whether irrespective of the size, a huge block or a small piece, the density remains unchanged. So the density is independent of the size. That is why it is an intensive property. Next, let us talk about the functions when the system is in transition. So there are couple of kinds of function, like the state function. A state function is a thermodynamic property of a system which has a specific value for a given state and does not depend on the path or manner by which the particular state is reached. So these kind of functions only depend on the initial and final state of the system. Examples are pressure, volume, temperature, internal energy, enthalpy, Gibbs free energy, etc. We will discuss this as we go forward in this course. Next is the path function. A path function is a thermodynamic property of the system whose values depend on the path by which the system changes from its initial to final states. Example, work and heat. Since values of path function depends on the path you use to arrive at the value, the path functions are not exact differentials. We'll talk about these exact and non-exact differentials in details later. So to give an example, say uh, you have to go from one end of a room to another end of that room, and there are some furnitures. You traverse a straight path from one end to another. You do not encounter any furniture and you reach the end. The amount of work you have to do, you can understand by the fatigue, whatever you feel, whatever little fatigue you feel. But let's say you decide that you will climb on every furniture again, then get down and take a zigzag route to the end of the system, you will feel much more fatigue. That means you have done much more work in the later case compared to the earlier case, and you can feel that by the fatigue you feel. Your journey, the beginning and the destination are the same, but the work done is different. That is why work is a path function depending on the path. So to summarize, we have talked about what thermodynamics is, what system and surroundings are, what are the functions and variables, and what kind of functions and variables are there. In the next class, we will talk about change of state of a system and other topics.